And so this class is kind of going to be like a workshop. So let's actually write programs. They're elementary cellular automata. Not very hard to write. You don't have to compute.
I didn't know. Should I go get it?
It's up to you. You don't like doing stuff. Right? So,
Alex likes to work.
it's totally up to you.
Okay.
Yeah.
Can I obtain the code?
You have
If I
many
need it?
friends in this class.
Okay.
So are you going to email us the code at the end of the Are you going to email us the code or not? Is it in our system?
We'll find out. It's not gonna-
Well, so like the zombie thing, I worked my ass off to get the code, and then the final version of the code was different enough that my original code was just an exercise. I mean, it's probably not a wasted exercise.
Yeah, that sounds like such a waste. Okay. So elementary cellular automata. So I will email you one of the programs we want to run. Okay. Elementary cellular automata. What do you think they mean by elementary cellular automata? Any idea?
Am I getting mine too fast?
Where is it on your desk?
Yeah.
So yesterday we had cellular automata, and we figured out that there were 512 possible rule sets.
Yeah.
So either the elementary one could either be the 512 rule sets, or they could be some kind of symmetry applied to that.
So that was in 2D.
So 1B.
1D.
Oh, yeah, for the element.
So in 1D, for any cell, I only have two neighbors.
Nice.
Cool. But we still have a surprising number of possible rules. Okay. What are the different states that these could be in?
So recall from yesterday, we can choose to say, are we choosing a two-state system?
So we have 8 possible current states.
Okay.
Okay. What are they?
8 states.
You mean for that 3 boxes?
Mm-hmm.
On off for each stuff.
Yep, that's 8. And what are they?
Off, off.
Let's start.
Oh, the combinations.
Yeah.
Yes. Right. Okay.
Let's start with 1, 1, 1. Okay. The next biggest number, 1.0. Room or 9.
Wait, so our cellular, these elementary ones are on a 3x1 grid always?
No, but for any cell, you have to look at 2 nearest neighbors. And itself, right?
Yeah.
Yeah. So that unit that we have to make a decision on is 3.
And our elementary always binary.
Well, if they're elementary, yes. That's part of the elementary.
Yeah.
So 1D, 2-state systems are elementary cellular. Okay, so these are all the possible combinations written in descending order. Okay, so that's the current state, possible current state. And then we have a rule that decides the new state for the middle cycle. Cool, because that's what cellular automata do. We saw that yesterday as well, so we had it too. So, we have a whole lot of possibilities here. how many total? How many different rule sets do you have? So on off, you have 8 possible current state. With 2 to the 8, 256. So there are 256 elementary cellular automata. Cool. People have looked at these 256, characterized them, looked at different things. Today, I hope to look at 3 particular rule sets. Okay. Next week, Wednesday, we'll look at a 4th rule set. And that is one that is amenable to studying traffic. Okay. But today, I want to just program elementary cellular. Okay. First one I want to look at is where, this relates to something we talked about last lecture. I want to have the rule set basically be an exclusive form. Okay? So, the middle site decides whether it's on or off, looking at its neighbors in an exclusive for type. Okay. What is the new state for the middle going to be for 111? Don't answer it. I want a second to think about it.
Independent of its own state. It's an exclusive for of its neighbors and doesn't.
Correct. 111 exclusive OR, middle becomes 0. Why is 0? Right, it's an exclusive OR. Okay, so both are true, it is 0. How about OR 110? What is it? 1. 101. 0. 100. 1. Let's keep going with Elizabeth. 011. 010. 001. 000. Cool. You guys know who Stephen Wolfram is?
You know Wolf from Alpha.
Yeah. Started in Mathematica. It's a pretty interesting fellow. Okay. He's very bright, industrious. And so really likes cellular automata. And wrote a book called Infinite Science based on cellular automata. And so the development of cellular automata is intrinsically linked and tied up to it. One of the things he did, kind of cute, we take our rule set, and let's just write down this number here. Okay? This is an 8-digit number, and we can consider it to be a binary in base 2. And if we can convert that to base 10, which I'm not going to do, you get 90. Okay? So this particular elementary cellular automata is known as Rule 90. Cool. We'll also talk about Rule 110, Rule 30, and Rule 184, which is the one that can be used in auto traffic. Okay. We're going to start with Rule 90.
Just like
Cool. So let's kind of predict what this is going to look like. Okay. And to do that, there's a very neat pattern we can generate. Let's take everything to be off except for one cell here. Okay. So this is at t equals 0. So everything else is off t equals 1 in some arbitrary time unit, what's the system going to be?
So it's going to turn off.
This guy is going to turn off, and his neighbors turn on. Oh, does everybody see that? Yeah? Okay. How about at the next time? Someone not Martin. What is it like?
Back in area papers. So you have the block E order.
Oh,
No.
because those are both on. And it's an exclusive or.
Oh, yeah, great.
That's off. How about this guy? Off. And it's symmetric. How about the next guy over? On.
Here's after the inclusive or, so if they're both the same.
Exclusive.
Okay, exclusive. Exclusive or, so if they're both the same.
You should have come to last class.
Let's do the
If they're
digital.
both 1 and 0.
Sorry.
But if they're both.
How about the next point in time? Someone not Martin or Amber. Austin is a not Martin or Amber.
So we're going to continue on. We're going to have the ones on the outside that turn off.
Okay. I'm not drawing all the blank space on the other side. How about this guy?
He'll be off.
How about this guy?
He'll be on.
Yeah. Good. Middle guy?
He will be off still.
Yep.
On. And then off.
And then?
On for the ending. So you have this kind of symmetrical pattern.
Okay. How about the next state?
Ooh, we get a repeat.
Well, these edges just keep growing out. Off. Is it? Well, his neighbors are on.
And we should apply it off.
Right? This guy, both neighbors are off. This guy, both neighbors are on. This guy off. This on. This guy off. We're back to just the edges.
Can I get a pattern?
Really? Okay. Next point in time, our edges are growing out always, right? This guy is off. This guy can be on now. These are all off because everything is off here. This guy is on, off. Cool. And then I'll just draw in the filled-in ones. On. This guy can't be on because they're both on. This guy now can be on. So this branch is going to be longer than it was when we had it. Cool. And in fact, it can be one more longer before we get where both of the neighbors are on. Cool. Has anyone ever seen anything that looks similar to this? And literally just seen this one.
Yes. Cantor set? Or something like it?
It's a special type of,
Fractal?
yeah. Which one? Sierpinski triangle.
Ah, yeah.
Remember how to form the Sierpinski triangle.
You take a triangle, and then fill it in the middle with an upside down triangle,
When you subtract, yeah, like that.
and then do that to each of the remaining. And then do that to each
Exactly. Et cetera, et cetera. Oh, I forgot.
Well, you forgot more than one.
Et cetera, et cetera. Okay. Fractal. Okay. What is a fractal? Pardon me? Yeah, so what's a more precise way of saying that? Because lots of things repeat itself. I mean, are you talking about just like a cosine function? It repeats indefinitely.
Smaller than our independent.
So at any scale,
You
looks
can
the
still
same,
find the same, yeah, same structure.
right? So self-similar. Okay, at any scale, it looks like it's the same at any scale. Cool. Any other examples of this self-similar type of behavior?
Oh, we did the random walk.
Random walk, awesome. Right, random walk, true random walk, until you zoom into your jump line. You zoom out at any scale, it will look like a walk. Okay. And so notice that ultimately, because it's discrete, you have a jump. Okay. We have the same thing here. Ultimately, we can't zoom in more than here. It's not going to look like this because it's discrete. Okay. But at all scales above that level, it will look like this. Cool. Any other real life examples of self?
Fluid. Like
Oh,
there's
yeah.
self-similar equation. Fluid flow between two plates.
Okay. Let's see if you're familiar with that one. But I trust you.
You're a fluid guy.
A common example is coastline, right? Oh, coastline. You look at a coastline from space, it's kind of jagged. Then you zoom in, it's jagged. Yeah, zoom in, it's jagged. Right? Ultimately, the most extent, it's a handful of sand molecules. Or scales above that. Cool. And a lot of structures in nature. Think of like tree branching structures. Cool. Fractal, self-similar. Neo, A. At least it was back in the 90s. Okay. So this is the discrete version of this. Okay. We can get even crazier. Okay. Anybody remember a thing called Pascal's triangle? Yeah. So, what does Pascal's triangle look like?
One,
One,
one, one,
one, one,
1, 2, 1,
1, 2, 1,
1, 3, 3,
1, 3, 3, 1,
1, 4, 6, 4, 1.
4, 6, 4, 1. We'll go one more.
1, 5, 10, 5.
10, 10,
10,
5,
5.
Oh,
Cool. So what happens if I erase all the even numbers?
You end up with something.
Oh, 6 is even too.
It's a lot.
Okay, it's the same pattern. Cool beans.
It is.
Can anyone see why this should be so?
I don't see what we're seeing.
This is the same pattern as this guy. Oh, yeah.
You're adding your two neighbors.
we should get images of
And what does that have to do with odd and even and
We should get that image
two
because
Because two odds make an even. Two evens make an even. Or not an even, it's odd.
and then
Neat. This wasn't really cool.
It
It
is.
is.
I was like,
Okay,
I didn't know that.
one more connection.
That it's just like,
Okay, one more connection. Let's take, I don't even know where to put it. Made my Pascal's triangle too big. Hold on. Yeah, put it down here. Let's take a random walker. Starts at this position. At the next point in time, what's the probability he's at this position?
is it six, something?
Yeah, P1 half.
Okay.
And the neighbors?
What happened?
Okay, the next point in time, what do I get?
Quarter, zero, half, zero.
Okay, next point in time.
8, 0.
Right? Cool. Well, notice that this, it's just Pascal's triangle, will be divided by the root number.
should be
Or 2 to the root number. Divide by 1, divide by 2, we divide by 4. Divide by 8.
Well, 2 divided by 2 goes 0. So some kind of modular.
Yeah.
It's kind of, there's some extra zeros.
There's extra zeros, yes. There's extra
But
zeros.
the idea.
Yeah, we're filling the blank spaces here with zeros. Cool. Yeah. By the way, this, what is this also? Probability successfully landing here after this many times. Probability of 1/2 is given by the. Yeah, this is the binomial distribution. Right. Where p equals 1/2. Cool. And then long time limit, what is this?
I think.
Yeah. Also by the center limit here, right? Get normal distribution eventually, right?
Oh, yeah.
Cool. Everything coming together here. What do we have up here? We have our normal distribution, our binomial theorem, our random walker, Pascal's triangle, fractal, and an elementary sublet automatic. That's all. Well, they're all, I shouldn't say that. They're all closely related. Because the systems. Cool. Neato Frito, hey? Yeah? Is everyone suitably impressed that I can move on?
Yeah.
Because I have to wait for more light bulbs?
So that last point, we're saying that the row in the random walk will eventually look like a gift.
Yes.
But we also
Looks like
said that
pattern,
it looks like what a triangle looks
We'll map it out the pattern there.
Yeah.
Then code it in.
like. Triangle looks like a gift.
Yes, so.
I just invite your phones.
Beans? You good? Martin's not good. But that's actually good. Let's program it and see what we get. Okay? By the way, there's other elementary cellular automata that give you Pascal's triangle. I haven't looked into these, but apparently Rule 60 gives it to you exactly, and Rule 101 is closely related. Okay?
So can we just like take a random rule and find like some like hidden passage of physics like behind it? Like,
Yeah, right paper.
like Rule 267, that's right there. That's how we figured out quantum mechanics.
Well, there are.
Yeah, there's Rule 60.
Specifically,
It might just sound that you're lying.
You can just keep adding, making it more complex. You never know.
I'm going to break the naming scheme.
There are people who try to do phone gravity.
Yeah, for sure.
They just multiply rules together until they get the answer.
Not necessarily from this point of view. But
Yeah, because they do it like the interference and not like that.
at the end of the day, it's not a great-
Rule 90.
So every rule is like important, has a cool name associated with it and everything.
Well, it has a number associated with that. I'm not sure they're all important, though. T max, let's make it 100. Int I to go over n. And int state. It's got to be have elements. Remember, cellular automata, we always have to look at the previous state. Okay, so we do things simultaneously. So we're also going to need an array where we copy in the current state into the previous state. Cool, so that we have a reference. All right. Pretty low-key program so far.
Oh, you did L.
I got my- Oh, you don't need some.
But nice.
Oh, I have a weird error.
Yeah.
Oh, now it works. Okay. So first thing we want to do is initialize. I equals 0, I less than L, I plus plus. State at L is going to be equal to 0 on. Okay? We're going to turn everybody on. And then we're going to say state at L over 2 equals 1. So we're just turning on the middle guy.
Will that work? Yeah, I guess we just write it down.
Well, we'll see. We'll see. Then the business end of our program is always the time loop.
That should be state I. Right. How about that?
Oh yeah, thank you. State I. State at I equals 0. We want to turn them all to 0. What is the first thing we want to do in our loop when we're doing cellular automata?
Copy.
Yeah. So let's copy this little loop here. And say P state at I equals state at I. And And then we want to loop over the cells and make our little decisions. Cool? So there's different ways of doing what we're going to do next. What I find handy is to define a left and a right interval, or integer, L and R. Okay? And these are going to be the index of our neighbor to the left and the neighbor to the right. Now our domain is obviously not infinite, so what can we do to have it be effectively?
Periodic.
Yeah. So what this means is if I doesn't equal 0, L equals I minus 1, else L equals big L minus 1. Cool? Sorry, not I. 1. Does that make sense to people? Cool?
Letter one or not? Little?
Yeah, maybe I
Yeah,
should have
okay.
named them left and right. People want these to be left and right instead.
That's a good code name.
What, to name it left and right?
I haven't really seen any comments yet. Really clear.
That's so messy. Cool.
Yeah, it's left and right.
And if I doesn't equal L minus 1, then my right is I plus 1. Otherwise, my right is, anybody?
Zero.
0. No, there's only one line.
Oh.
Great.
Cool, so we have our markers. What's our next step? Anybody?
Evolve. Apply the rules to our current. So.
Yep. We have to make a decision of what to do with cell I. That's the one we're looking at. What is that decision based on? How? What about left and right?
P state of left and P state of right. And XOR.
XOR of them. Okay, C plus plus is an XOR version. So how can we write it out? Yep.
Maybe like a P stage.
Well, I mean, we could also
That
do
one line.
P state left plus P state right.
Yeah, that's a very nice way to do it. Okay. The other way is to have an OR. And an AND. Make sure they
no,
aren't.
right.
Oh, thank you. To make sure they aren't equal. That's missing a close brackets. Okay, so that's an exclusive OR. Martin's suggestion is obviously nicer. This is explicit what exclusive OR. So what do we do if this is true?
And then one.
Else? That's it. Should be our program. Where did I screw up?
You need to link map.
Oh, I got mine. It's just giving me a warning. So I should put brackets around this or statement.
Yeah. And you can also use just an actor.
What was wrong?
We have to put brackets around this or statement so
Yeah.
that it's evaluated on the same level. And so that this must be true, this or statement must be true, and this must be true.
Yeah. But that's just logical. That why it's giving you that?
No, it's giving me a warning.
Oh, warning.
Yeah.
That's how big it's
Yeah. That's how good compilers are now. They can check when your logic is.
pretty sure you need this instead. That's right. Go how did you?
Okay. So we want to visualize our results. Okay. You don't need to bother using DMD for this. I think they're not quite that difficult. So let's just make an out file. And I'm going to name it a PRN just because that way I can load in our program and visualize it. And I'm going to output, when I do this loop where I copy the state, I'm also going to output the state to the file. Okay? F print F out I, and then just a space, not an end of line. State at I. And when that's over, then I will end the line so that it's on a new line for the next time. Cool? Everybody all right with that?
So
I'm just writing the state to a file. So it's going to be a matrix where each row corresponds to a successive point in time. And each column is just cell location. Everybody okay with that?
Which, oh, just the space. Okay. I thought you had to make another addition. I got a second.
Ooh, ooh. Did you make a file?
Yeah. I think so. Yeah.
Okay. How's everybody else doing? Everybody compiling?
Blur your eyes. Blur your eyes. Look at that from this angle, actually.
So you got a slicer for the eye? No.
You can see the triangles.
Otherwise, you
Right?
I just had on the file.
in the file, right?
Oh, yeah.
Didn't we write it?
You actually get back to particle management.
Like a second, man. Do you know
Yes,
how
it does.
do you know how to output unit?
Yeah.
But did it run?
Yeah, I was doing it all.
Oh, okay. And so what does that look like? So in this package, I can make what's called a picture. What I can do is multiply all the values by 255. Because it's it. Build the matrix up here. And that's the pattern again. Cool, hey?
Yeah.
Pretty nice pattern, eh?
Looks like something we just did on board.
Yeah, exactly. And it's also related to. Okay. Pretty neat, eh? So this is just a really simple program. I mean, that took us like 10 minutes to code. Okay, and you can do pretty cool stuff.
Nipplot does it?
Cool.
Where is
That's these guys. That's these guys. How are you guys plotting it?
Nipplot does it?
Oh, I just looked at it in the
I just
paper.
added the file.
Yeah, but you have a big one.
They're in the paper.
Just printed it out.
Big.
with the button there.
Worked.
Oh, so you're doing like the matrix.
Like, yeah, just right there. No marks or steps.
Have you
here,
done
anything.
Open Nipplot, you can do set view map, and then S plot file matrix with image map.
What is this in?
Nipplot. S plot, and then single row file name.
Oh yeah. So
Matrix.
this is really nice. Things don't always look like that. So instead, what do you got there, Kyle? You're very proud.
And printed instead of printing a one here, I printed a block here.
What did you do?
For the zeros, he printed blank spaces, and for the ones, he printed block
Like a
squares.
Unicode square. Oh, nice. That's a Unicode. Nice.
Nobody else can. Showing everyone up.
I got a color bar.
ASCII art's sweet, man. Okay, so let's try initialization. I'm gonna pull a random number.
I finished my task.
If the engineer's great.
Let's just start with a random initial condition.
We change. Should we be following?
If you want. Making a random number. RND.
Or
That's not working. Oh, that's fine. And so I'm just initializing it from a random state now. See what it looks like.
So the initial state is 50 chance that every bit.
That's right. Okay, and we still kind of see these triangle shapes that are coming out, but it's obviously much more Random. Not quite as well ordered as the past. Cool. Good.
Also, for the one that the triangle that did work, our periodic boundary. That's a lot of valuable people.
Yeah, we did. So, like, what are they doing?
Well, it just surprises me that we actually got the triangle. Because we've actually wrapped around on it, so our triangle is disappearing with itself.
Well, I don't know about that. Yeah, I mean, that might depend on the length you choose and all sorts of stuff.
Yeah.
Like constructive interference.
Yeah, but it still looked a lot.
Yeah, that's like.
Well, maybe if we ran it for longer.
Yeah. Cool. Everyone's suitably impressed. It's pretty neat, eh? That's not very much code, but you can do cool things. Okay. Let's look at some other examples. So, this is our next rule set, okay? Rule 110. Let's rename our program, be 110, and rename our data file so we don't overwrite some triangles. How can I go about programming this one? So remember, and make sure you remember this for your final exam. Always cannibalize your own code. Okay? Save you time. It's not cheating to not start from scratch. Oh. Okay? So we're going to use the same framework here, but what do we have to change?
So we got 90 because we used the XOR gate. So what is rule 110? Is that the end?
So the difference between rule 90 and rule 10 is the
110.
binary 2, binary 10. So the binary 2 gives different exclusive words, and that changes how we talk.
So remember where the name comes from. Okay? Always write down the possibilities in this order. We then write down the new state in this order, and then convert this number to base 10. Yeah. And that gives us a rule. Cool?
Okay.
Which is 256 possibilities. This is an 8-digit number in binary. It's obviously 2. Right? Cool. Rule 110 is this, that this goes to this, this goes to this, this goes to this, this goes to this. Let's say, it's not a specific case.
It doesn't follow anywhere I say. It doesn't follow. XOR.
Or do we just do a bunch of it?
Yeah,
Is that how we're going to do it?
this isn't simply an X or an and. It's just rule 9. Okay.
If you know, like, what you have, you can go backwards and figure out how Yes. Divide the 1 point times base 2.
Yeah.
And I go back.
Yeah, absolutely. Absolutely. Yeah. Yeah. But it's all right there. So we just have to figure out how we're going to implement these rules. Previously, we just had this nice statement here, which was an exclusive OR, right? We can't do that anymore, so what should we do? Taking suggestions.
We could write a statement that, I mean, the long way is write a statement for every case.
Yep.
That would be the long way. You could probably double a couple of them up.
Switches are tricky though, right? Because switch has one condition. Here we have 3 things that can have different conditions.
We can convert the current states into their decimal number. So we have these switches.
Yep, that's a very nice way of doing it. Okay. Not necessarily the most obvious. It's a very good way of doing it. Let's just do it like stupid brute force for now. Okay, but let's break up our trees. Look at the word.
Well,
That's also true.
we could figure out what
I thought that was a rule
That was rule 90.
So why did you change? Like what?
Because this isn't rule 90 anymore. This is rule 100.
What is going to change? Because I thought we were using that as a way of evolving it. So like,
Yeah, but now we're using a different rule set as a way of evolving. These have changed now. These are no longer. This is no longer the number 90.
But how are we changing?
This way. This state goes to 0. This goes to 1. This goes to 1. The same.
You can convert the 1 times base 10, or the 1 times base 10 to base 2. You'll get the 8-digit number. That 8-digit number will signify how your states will change from 0 or 1 on 1 to 1 on 0, 1 to 1. If you think about it.
I'm just gonna watch this play. I'm not sure.
So we're just changing the rules.
Yeah.
And you can view it as totally arbitrary rules. Okay? When we have this state, it goes to 0. Okay? When we have this state, it goes to 1. Okay? When we have this state, it goes to 1. If we have this state and it's an exclusive OR, what does this go to? It goes to 0. Okay? So this is not rule 90. It's not an exclusive OR. Okay? If we have this state, it goes to this. If this was an exclusive OR, what would this go to? 1. Those are not an exclusive.
We're just defining a new bit rule.
What it is, I don't know. It's equivalent to a Flooper game.
Okay. Yeah.
Okay. It's just a bunch of rules, man. So let's do. Let's just divide it up for our own sanity into whether our current state is alive or dead. For the central one, the one we're looking at. Okay? And then we have 4 possibilities in each of these. So if left at I and right, if P states at left and P states at right, what do I do?
You're missing a square brace at the end of the state. So if your initial state is 0,
Well, actually, let's make our initial, let's first look at all the alive states. Okay. So our central cell is alive, so are both, or it's 1. I'm playing with Kane like, and both the left and the right state are 1. What's my new state? Yeah, I have 1, 1, 1. What does 1, 1, 1 go to?
Right, so we don't need the equals one. And
That's right. This can just be.
Yeah.
Cool. If P state left and not P state right, then what do I do?
Stay high.
Oh yeah, thank you. Right, because that's a condition where I have 1, 1, 0. Is everybody following this? If P states, if not P state left, and P state right, then what do I do? So that is 0, 1, 1, right? Which is 1. And if not P state left and not P state right, then what do I do?
one.
Right, because that corresponds to the state 0, 1, 0, which gives me. Cool? People all right with this? Okay? So since it's not so easily equivalent to a logic gate, we have to be more explicit about this. And there are much better ways of doing it. This is relatively obvious. And so now I can do the exact same thing for all the cases where my middle state is dead. So this one corresponds to 1, 0, 1. What do I do for 1, 0, 1?
1.
What do I do for 1, 0, 0?
0.
What do I do for 0, 0, 1?
1.
What do I do for 0, 0, 0?
0.
Yeah. That should be it. Sorry, I'll switch back to that. Just want to make sure I'm actually close.
Yeah.
Did you figure out the logic?
I didn't simplify it, but I
All right, cool.
wrote down
Right on.
this early.
Right.
Okay, we good? So let's see what happens. Run it. Everybody okay with the program? Yeah? Okay. So we started with an XOR gate because it was really easy to program. And then this one is not so easy to figure out exactly how to do shorthand for it. But even if we do it explicitly, it wasn't that much. Okay? See what it looks like. Yeah, this is still the random number.
That's good.
Lucky, eh?
1,000 would be 2 bombs.
That's right. That's right, we can make some nice bit art here. Where it says Russia over ISIS.
It seems to be converging. Wait, it's starting at the top or starting at the bottom?
Starts at the top.
So, well, not quite converging. That would be stabilized.
So this rule is neat because it lies at the border. It displays both ordered and chaotic behavior. Like we saw with a bunch of the ones yesterday, like game of life. They can be both ordered or chaotic. Okay? And interestingly, this simple rule set That's also been demonstrated to be Turing complete. Okay? That rule set, in theory, can do any calculation that any can do. Just that rule set. It's enough. Crazy, eh? Isn't that crazy? I think that's crazy. Okay, so super simple behavior, elementary cellular automata, making it really complicated dynamics and results. It's kind of the theme of this course. Okay. Any questions on this? Everyone's doing all right? So we can play with the initial conditions, right? And see what changes and what stays the same. I haven't really done that yet, so I don't know what would make this.
Wolfram does this. I typed the first 2 months. And Wolfram into Wolfram, and it's like rule 254 elementary cellular automation evolution. So, wait, so talking about
You did something wrong.
no, I only did the first 2.
Oh.
Yeah.
So it identified the elementary cellular automata.
Yeah.
That's hilarious. That's impressive.
Yeah.
Well, keep going. See if you can actually do it. Go the full way.
See what I did?
That's really crazy, actually.
Cool. Good. Okay, so to finish this off, so yeah, so that one's neat. It's actually been demonstrated to be Turing complete, which is pretty great. Okay, let's finish off with one more cellular automata, and then next class we'll come back and look at a different rule, which is rule 184. Okay, and these rules aren't going to be as arbitrary. We're actually going to see that we can give physical meaning to the rule set pretty easily. And from that physical meaning, we can then use it to model traffic. Cool? Okay. So what I want to look at is rule 30. And actually, before I do that, I want to test one thing with this rule.
Make the whole thing one.
Yeah. I want to start with a really uniform. Nothing.
Do we just get one row of white and then everything else is black?
I guess so.
Yeah, because if everything is white, so the new rule is just zeros right across, and then after that it's zeros. And
Yeah. Hold on.
Right. So now let's take.
is single one at the very start. See if it propagates forward. Okay. That's really cool.
Wow, so we can see the propagation of that thing.
Definitely getting some optical here. The top looks like the white is darker than the middle.
So literally there's a yellow tinge the lower you go.
That's probably the projector.
No,
That could be a projector.
Oh, you guys aren't seeing the whole thing. It's being cut off for some reason. Oh. There's actually kind of a little ticker tape on the side here.
Oh.
Yeah. I think this is some kind of binary code that makes the secrets and interest of the travel.
see?
Yeah. Sweet, eh?
We just need to pick the rule and prove that all mechanics comes out of it.
Neat. We all good? So let's try rule 30. Okay, so rule 30, we can definitely keep the same structure we have here. And all we have to do is change all these things, okay? So this state is state 111. In rule 30, what does 111 become?
Oh,
0.
0, 0, 0.
This is state 110, and what does 110 become?
0.
This is state 011. What does 011 become?
State 0 and 1 is 1.
It's 0, 0, 0, 1, 1, 1, 1, 0.
Yeah. 2, 4, 8, 16, 68, 20.
Oh, no. That's good.
Yeah, no, you're fine.
No, I'm not. I'm missing one.
So that's your
Which,
no, it's not your state. Over.
which,
Okay, so let's do the multi-testing.
Yeah.
That is
the,
the state I
binary of
It is 30. Okay. Cool. What's that called?
Wolfram here.
Okay.
Probably it. See it. If you type in like rule 110,
Yeah.
it'll give you the algebraic form.
Oh,
Yeah.
cool. That's really neat. And so that's the logic. Yeah, the Boolean
That's the Boolean
part
part,
of
but
that.
that's the single statement.
Yeah. That's very cool. Yes.
So I guess as you said,
wow, it says cellular automation rule 110.
So let's start.
Let's go ahead.
Everything's 0, and the center cell could be 1 for rule 30. And let's see what it looks like.
How many propagation?
That doesn't look right.
Can you go back to the code?
Oh, we didn't finish doing our rules.
Yeah.
So 111 was 0.
It's 0,
1100.
0,
011 is 1. Right? And then 010 is 1. Okay. 101, 0.
Oh, you got it.
And then this is
0,
100. That's 1. This is 001, which is 1. And then this is 000, which is 0. So incidentally, the one we just looked at, we can figure out what rule set it was that we said nice.
We can just throw them in and then change.
As Matt pointed out.
Cool. Okay. So pretty funky shapes.
Hmm. Neat. Yes, no, maybe. Okay, so rule 30 is chaotic.
So how do they define chaos for these discrete problems?
So they look for repeating patterns. Perform analysis on it, look for repeating patterns.
So there's no repeat pattern?
That's right. So Wolfram Alpha has actually used rule 30, looking at the state of the central cell as a random number generator.
Where?
Yes and no. Yes, but it may not be the best random.
What do you mean?
A random number generator, you want to quantify how well distributed your output.
Oh no, I know what you mean by that. But you mean they implemented cell for this. Is it the same every time?
Yeah, no, but the state of the central cell here flips around randomly.
Oh, so if you rerun this code, it'll be different?
Nope, but you cannot predict what the state of the central cell is going to be.
Is that right?
Yeah,
So if you
given
look
all the
at, if you look
previous
at
history.
cell middle every single time, that you can't tell if it's going to be
How the hell do they do
I don't see how it's a random number.
Well, there's your randomness. What else do you want?
But it's predicted.
that? It's deterministic, but also the random number.
So don't forget, chaos is deterministic. Right?
Yeah, no, okay.
So the point is that if I say I'm going to pick a number, it's going to be the 18,413th state of the central cell of the simulation. You can't tell me how to number it.
Oh, you mean the cell in the central column?
Yeah.
Oh, okay, that makes sense. I thought you meant they picked one specific cell
No.
and use
No,
that all the
it
time.
changes.
Okay.
as a function.
Okay, that makes sense.
So that would be a random constant.
Yeah.
Zero. How about now? Still zero.
Nice.
Cool. Let's play with this a little bit again too with the initial condition. Let's just put this at 0. Okay, for the periodic boundary conditions, we have it going from both sides here. Okay. Neat. Want to do our random thing? Okay, looking pretty random. There are characteristic patterns, okay, but overall it's not predictable what this is. Cool. This is the chaotic cellular of that. Cool. Yeah. Fun. So for the assignment, for next week, how about we do this? We've looked at a lot of cellular automata, some elementary ones, and some not so elementary ones. So how about you guys pick one of these not elementary ones and code it? Cool?
A not elementary.
Cellular automata. So you can do Brian's Brain, you can do Game of Life, you can do Wire World, you can do Langston's Ant.
Oh, so pick one that's known in the program.
Yep.
Just reproduce the known thing.
Yeah, and they would reproduce something interesting. Tell them why it's interesting. Cool? Is that fair enough?
Is the right way to say it, pick a cellular automata or a cellular automaton? I mean,
Semantic,
is each cell
really.
an automaton or is the whole system an automaton?
Martin, it's one system, it's an
Look at
automaton.
the pretty pictures.
It's a single system, therefore it's an automaton.
I guess a single would be cellular automaton.
A cellular automaton is a collection of colored cells.
Okay, so rule 30 is
A cellular automaton.
no, actually, the cellular automaton has information for it.
Yeah.
So that picture is a picture of the cellular automaton.
Yes.
Automaton.
Cool, does that sound good? We'll just explore one of these non-elementary ones. Make something cool. It doesn't have to be super fancy.
Cell point of gravity.
Yes. That would definitely be super fancy, but not required to have it.
Yeah, you can go, you can,
I don't have.
congratulations, Martin. I, on the other hand, will focus on not making some algorithms.
But let's not do Rule 184, okay, traffic stop. Okay, because we're going to do that in class.
Well, we can do any of these.
Yeah, you said non-element.
No, I know, but you can expand Rule 184 to include things, and you could argue and say it's not elementary. You can argue with it.
So I can take a 3-state rule 30 system and make it non-element.
What happens?
I suggest you take one of the ones that's written about on places like Wikipedia and just explore.
Yeah. Sounds good.
What happens if you go higher dimension?
3D cellular?
Yeah, it's like these rules, but up, right now you're only looking at nearest neighbors, but what if we extended it 2 more bits, looked at above and below.
Yeah, so you can do that as well. You can also extend the rule set by looking at next nearest neighbors.
Oh, next here.
Yeah, and then so these have names as well. Like that neighborhood, I forget what that is. Right? So, they make it more complicated.
Yeah.
Find one of those that's interesting. Cool.
Yo. I think that would work. I'm not using C. I know.